The objective today is to learn all about wave and wave phenomenon vocabulary. There's all kinds of waves. You can think of sound waves, light waves, water waves, and there's others. But let's start with the basic definition of a wave. It's a disturbance, a wiggle or jiggle, that transmits energy without the transmission of a physical material. This is the main thing you got to keep in mind with waves. They transmit energy from point A to point B without transmitting any physical material. The physical material itself that the wave travels through is called the medium. The particles in that medium just wiggle and jiggle. They end up going nowhere. They go backwards and forwards, backwards and forwards, backwards and forwards, but they end up going nowhere. Net displacement is zero. Or they might be going up and down, up and down, up and down, up and down, but net displacement is essentially zero. For example, for water waves, water is the medium. For sound waves, typically air is the medium. The air particles just vibrate. When I talk or you talk or anybody makes a sound, the sound travels through air. It can also travel through solids like, or liquids like water or even walls that are solid. But the particles in these medium, speaking of air, there's air particles, little molecules. All they do is vibrate. As I talk, the air from my mouth is not going to your ears, or when you talk to somebody in a room, the air particles are not going from one person to the other person. It's the vibration of the air particles that bump into one another. It's kind of like a domino effect, which I'll explain a little bit more with some demonstrations in class. Another example is like the wave, quote unquote, the wave at a football game or a soccer field when you have a full stadium. Some of you have probably done this before. What would be the medium as the wave goes around and around the stadium? Well, in that case, the medium, the substance through which the wave is traveling, are the people. The people are going up and down, up and down, up and down, and the wave is going around and around and around. There are a couple of ways to categorize waves. One is to separate them into mechanical versus electromagnetic waves. Mechanical waves are waves that require a medium. Water and sound are both good examples of mechanical waves. Water waves need water to transmit through a physical material. Sound needs air or water or some material substance to travel through. They require a medium. Electromagnetic waves, sometimes called EM waves or EM radiation, do not require a medium. And some good examples of that are light, radio waves, X-rays, and there's some others that we'll get into later on. But there's a whole electromagnetic wave spectrum. The lowest energy would be the radio waves, which are not harmful, but some of the higher energy, like X-rays, are harmful. That's sometimes why we call it radiation. But there's a whole spectrum of electromagnetic waves that do not require a medium. In fact, most of the time they prefer not to have a medium. But there's still something vibrating, and that is the electromagnetic fields, and I'll expand on that idea in the next unit. But for now, there are mechanical waves like water waves, sound waves that require a physical material to transmit through, an actual physical medium, and electromagnetic radiation, which is a wave. It's an energy that's transmitting from point A to point B through the vibration of a field without transmitting any material substance from point A to point B. So that's one way to categorize waves. Another way to categorize waves is to split them up into longitudinal and transverse. Once again, you can only be longitudinal or transverse, just like you can only be mechanical or electromagnetic. You can't be both mechanical and electromagnetic. But longitudinal, the particles of the medium, when there is a medium, vibrate parallel to the direction that the wave is propagating or traveling. A good example of this is sound. It's probably the best example. When you talk or anybody makes a sound, you're causing air particles or water particles, if you're underwater, to vibrate forward and backwards, as the wave energy itself travels forward and outward. But once again, the air particles don't transmit from point A to point B. It's just a vibration. It's kind of like a domino effect, once again, where the first particle hits the second particle hits the third particle hits the fourth particle, and it's a chain reaction, but they bounce back and forth, back and forth, back and forth, end up going nowhere, but the energy, the sound energy, transmits forward and outward from point A to point B. Now the more common type of wave really is the transverse, where the particles of the medium vibrate perpendicular. To the direction that the wave is propagating. Once again, I'm trying to avoid using the word move. Try not to use the word move when you describe waves. The word move can be very vague. We want to talk about particles or fields vibrating up and down, like in this case. And this is the most descriptive type of wave, or the type of wave that you most often would draw. If you draw it down here in the next section, you'll see a diagram of a transverse wave. It's the easiest kind of wave to draw, like a water wave, because water is a transverse wave. Light is a transverse wave. At a football game, when you have people doing the wave, going around and around the stadium, that's an example of a transverse wave. The people are going up and down, up and down, up and down. The energy of the wave is going around and around and around the stadium, perpendicular to the way the people are vibrating. So let's look at the diagram here. Basic wave vocabulary. This diagram depicts a transverse wave because it's the easier kind to draw. It's kind of what water waves look like. In the next unit, we'll draw a longitudinal wave when we talk specifically about sound. But for now, let's concentrate on this diagram. Here are some things to keep in mind. Waves have a crest. Transverse waves have a crest, a top spot, the high spot, and they have a trough, the low spot. Waves have a wavelength, as you see marked off in the diagram up here. Let me circle it in red. Now, one of the hardest things about wavelength is the symbol we use for that. We're not using a W, we're not using an L, we're using the Greek letter lambda. L-A-M-B-D-A. It's kind of like a backwards H. And it's kind of hard to remember, especially because it's not an English letter, but you'll get used to that. And it literally is a length. Its units will be meters, standard units. I mean, you can do it in inches or miles or feet, but we're going to use meters like we always have, and you can do it in centimeters, millimeters, but meters are the standard unit. It's a length. It's how far it is from one point on a wave to the next corresponding spot of similar type. For example, if you measure from one crest to the other crest, if I measure from this crest right here, the top of this crest, to the top of this crest, that would be the wavelength that's marked off on that diagram. But you could also measure from any other corresponding spot to another corresponding spot. So for example, right here, that corresponding spot to this corresponding spot would give you the same wavelength as from crest to crest, or you could do it from trough to trough. I can measure from this trough down here to this trough down there, and once again, that would give you the wavelength lambda, the same in all three different measurements. The amplitude, with a capital A, is the distance from the equilibrium, the rest position of the wave, like that middle line, and if you've done this in math classes, like the x-axis, to either the bottom of a trough or the top of a crest. Right? Don't make the mistake of measuring from the bottom of one trough to the top of another crest, because that gives you double the amplitude. But amplitude, once again, is measured in meters. It's a length, basically, or height. So the units are meters. We're not going to do a whole lot of measuring of amplitude, but we will do quite a bit of measuring of wavelength. All right, so the symbol just down here is supposed to be, the symbol for amplitude is A. All right, period. We've talked about that first semester. The period, capital T, is the time it takes to make one complete cycle of anything, but in this particular unit, it's the time for one vibration or one cycle of the wave. The standard units, because it's a time, standard units are seconds. Now, frequency, which is often confused with period, is nicely symbolized with an F. It's the number of cycles occurring each second. The standard units are cycles per second, and we have a name for that. It's called a hertz. H-E-R-T-Z, abbreviated with Hz. It's just the reciprocal of the period. So let me summarize again. Waves have a wavelength, how far it is from one corresponding spot to another corresponding spot. An amplitude, basically how high they are or how low they are from the equilibrium position. The period, how long it takes to make one wave before the wave repeats its cycle. And the frequency is how many cycles per second, measured in hertz. Let me give you a mathematical example. From a mathematical standpoint, t, the period, is equal to 1 over the frequency. And algebraically, if you move things around, what that also implies is that the frequency, f, equals 1 over the period. They are reciprocals of each other. If you know one, it's pretty simple to calculate the other. For example, if the period is 6.3 seconds, calculate the frequency. Now you can use either equation here. They're equivalent, but if I take the second one, the frequency will be equal to 1 over the period, which is 1 over 6.3 seconds. That's standard units. My answer will come out in standard units. F comes out to be equal to 0.16 cycles per second, 0.16 cycles per second, but I can call that 0.16 hertz. And you can leave it as cycles per second, I don't care, but the official unit is hertz. But that means cycles per second. Alright, second example. If you got the frequency, calculate the period. Once again, you can use either equation, but it's most direct to use the first equation on the left-hand side over here. T equals 1 over F. Now watch out here because this is 23 kilohertz. You can say 23 times 10 to the third because the K, always watch out for the kilo here, that's the K, that means 23,000, which is 23 times 10 to the third. So the period here is going to be really, really small. It's going to be 1 over 23,000, which comes out to be 4.3 times 10 to the negative 5 seconds. The most common mistakes made here are getting these units backwards. Period is in seconds, frequency is in hertz. It's a pretty straightforward problem to calculate one if you have the other. You always just take the reciprocal. Just watch out for units. Make sure it's in standard units and make sure you have seconds for period and hertz for frequency. So that's basic wave vocabulary. You have the wavelength, one corresponding point to another corresponding point, the length, the amplitude, how high or low the wave goes from equilibrium, the period, how much time it takes to make a wave, the frequency, how many waves occur or vibrations occur per second, mechanical waves versus electromagnetic waves. Mechanical waves require a medium, electromagnetic do not. And then longitudinal versus transverse, where the particles in the longitudinal wave vibrate forward and backwards in the same direction that the wave is traveling, where they back and forth in the same direction that the energy is traveling, and transverse, where the particles in the medium vibrate perpendicular to the way the wave is traveling. But in all cases, the main descriptor for a wave is that energy is being transmitted from point A to point B without a material transmitting from point A to point B.